I'm Brad Ashley. I'm the Director of Business Development here at Solve 3D.
And I'm Scott Campbell. I'm the CEO here at Solve 3D. And Brad, we're into video 2 of the object classification using deep learning on LiDAR. Boy, that's a mouthful. What's this video going to be about?
Yeah, so video 1 was covering the training data, and here in video 2, we're going to be actually training a model and going through how that works. Before we get too far into it, though, Scott, we did have some questions that came in, and I thought we should do a quick recap on the training data itself.
Yeah, that's probably a good idea. So first of all, let's talk about that overall workflow. It's a 3-stage workflow. Video 1 was about step number 1, which was preparing the data and making sure you had really good training and validation data. Brad, I think you might have a little example here of LiDAR specific data that we can look at and talk about.
Yeah, here we have an example where we have some points that are run through the data that are unclassified. So if we keep this data, in a small amount, it probably won't be an issue. But if we've got, as you're seeing on the screen, a large amount of unclassified points that are running through the ground data, you're going to have issues with that ground classification. And so we recommend that you deal with this unclassified data. Very similarly, if you had data that's incorrectly classified, maybe you have a building that's classified as vegetation, or you've got a tree that's classified as a building, you'd want to clean that up. And if you've got probably 10 or 15% of your data set in that case, in that way, it probably won't be an issue. But when you get into that 30, 40, 50% of your data being incorrectly or unclassified, it's going to cause some major issues.
Yeah, I think of it like teaching or training a person. The training data is meant to give example of, this is what I want you to recognize. This is what I want you to recognize. This is good. This is good. This is good. But if you're actually giving the model training data that is, well, this is good, but it's actually bad, then it's really confusing. It'd be confusing for a person. So it's not a black and white kind of thing. It's a bit of a grayscale.
Yeah, that's a good example there, Scott. Now that we have our training data ready and prepared, and we start to go into the training of the model, I did want to mention that we recommend that the data be split into 2. And in this case, what we're recommending, as you can see on the screen, is a 66% split and a 33% split. So 2/3 of the data ready for training and 1/3 of the data ready for evaluation. And the reason for that is that as we go through the training here today, you're going to see that the training data tests, and then it goes and tests the evaluation data equally. And so it's back and forth going to see how the accuracy and the loss of both of those data sets are. So that's why we recommend, again, splitting that data before you start running it through the algorithms.
I think of Brad as like the validation or the evaluation data is like a pop quiz in school. So, the training data, you're using that, you're doing your exercises, and the teacher comes along and gives you a pop quiz. That's what the validation data is for. That's the data for that pop quiz. So the learning algorithm actually has a chance to test itself to see how it's doing, to know whether it's getting better or worse. And I think we'll see that a little bit later when we talk about the tensor boards.
Yeah, great. Scott, in the last video, we talked about why did we choose deep learning, and we went through, the reasons that we saw. Now that we're into the training, can you explain a little bit about the algorithms that we're specifically using?
Yeah, so the algorithms are what are used to create the trained model that you'll use for classification. In this case, we went through and we looked at what was available out there in industry, and we settled on PointNet from Stanford University. They really were a pioneer in applying these techniques to point sets or point clouds. And the latest version of their work is PointNet++. So that is at the heart of our framework, and it's a really, really good framework. But it does drive something really important. This framework requires some significant computing power. So maybe we'll just flash up here, Brad, the minimum system requirements. And when we say minimum, we really mean minimum. You do not want to try to run this unless you have a computing environment that has this sort of requirements or specifications. And this is listed out in the handbook as well as the user guide. So you're going to want to take a hard, cold look at your computing environment about what you want to run this framework on before you actually go to run it. In fact, we would recommend this set of requirements or this set of specifications for your computing environment in order to have something that's It's not going to take 20 days in order to run. So take a look at these specifications. They're in the handbook. And once you've got that all set up, you can jump in and do as Brad's about to do, which is to actually run the learning algorithm.
Yeah, great. So here in Solved Engine, you'll see that we now have a new set of tools. So on the left-hand side, we now have a new set of tools called Training and Detection. And underneath that category, we have 4 specific tools. The one that we're looking at here today is the point cloud training. So as you select that, it comes up in the operation. You'll be required to select that training data. Again, that would be the 66%, as I mentioned, as well as the evaluation data, which is the 33% split. Once you've done that, you can start to do the inputs. All of this is in the handout, and I recommend you look at the handout to figure out what you should be putting in there. But once you've done all of that, you simply select the output folder and you start to train. Now, as the training starts to go, you'll notice that the tensor boards do start to pop up. And in the early stages of this training, they're going to be a little bit jagged, and you're starting just to see the accuracy and the loss of the data.
Yeah, that looks a little rough there.
Yeah, and as we go through a little bit further, you're going to start to see that we're getting closer to that 95% accuracy, which is what we really are hoping for on both the training and the evaluation data. Also on the bottom, you're seeing the loss. That's the loss of the data that goes through as you're doing this training.
Yeah, it's starting to come in there. I can see it there. Yeah.
As we run this specific data set, we're actually using a computer that uses the recommended specs, as Scott mentioned, and it does still take about 8.5 hours to run the training. And so, as we said in video 1, the training of this is really where the time commitment is. And then after the case, the classification of the unclassified data is fairly quick, and we're going to see that in video 3.
And of course, Brad, the beauty is that you can, 8.5 hours, you can run that overnight. I mean, you can set this up to run as you're leaving work for the day and come back the next morning and this will be done.
Yeah, that's right. It doesn't require any human interaction there. It really is running on its own. So once you've got that training model done, that's when you would save it. And Scott, what are you thinking about the saving of these models?
Yeah, it's a really good practice in software, but certainly in this case as well, in deep learning, to have version control on the model, which is to say every time you save it, give it a version number, and in the maybe even in the title of what it is, make a nuance. So if you were doing this for the fire hydrants that we talked about in video 1, you might say, Chicago fire hydrants version 1. And if you then go back to try to update the model with fire hydrants from Paris, you could say Chicago/Paris fire hydrants model 2. And that way, if you've got that version control and you have different versions saved, you can actually revert. So if you find that, oh yeah, listen, the model did not train very well, my testing is disastrous, you can actually revert to version 1 of your model and not to be too fussed about it.
Yeah, that's a great point, Scott. And here we'll pop up the key point summary for this video, which is that version control. If you feed it the wrong data, if you feed it data that you thought was really well classified but wasn't, and things start to go sideways, being able to go back to that previous version is critical, both for the model itself, but also for the timeline of your project and ensuring that you can stay on top of that stuff.
Yeah, absolutely true that. So if that's the key point summary, Brad, then I'm guessing that's the end of this video. So what are the next steps here?
Yeah, this is the end of video 2. We now recommend that you take that data that was sent over, the sample data, and run it through a training algorithm of your own. See if you can get similar results. Look at the tensor boards that you saw here in the video and see if you're getting similar accuracy and loss on the results that you get. Once you've done that, we'll do a quick check-in with you probably in the coming week to see how those results went. And then we're going to recommend that you move on to video 3, which will be the classification of the unclassified data sets.
All right. Well, Brad, I guess I'll see you in video 3.
All right. Thanks, Scott.